Hi students, previously we discussed the corona where the voltage is where it is observed for high voltage transmission lines, so that we discussed two voltages like disruptive critical voltage and visual critical voltage. So whenever the operating voltage is beyond the disruptive critical voltage or visual critical voltage, we can observe the phenomenon called as corona. So in that, one of the voltage is disruptive voltage. As of our definition, it is the minimum voltage. It is the minimum voltage at which the breakdown of air occurs. So whenever the air around the conductor starts ionizing, that voltage, corresponding voltage, is called as disruptive critical voltage. So it is the minimum voltage at which the ionization of air surrounding the conductor takes place. Okay, and the corona formation starts. Such a voltage is called as disruptive critical voltage. Therefore, how to find out this disruptive critical voltage VD is a next our discussion. So it depends upon the gradient, potential gradient of the conductor which is available at the surface of the conductor. So as per our discussion, the potential gradient at the surface of the conductor is given by a mathematical formula G, which is equal to V by R into ln of d by R, where V is the operating voltage, G is the potential gradient on the surface of the conductor, R is the radius of the conductor, D is the distance between the conductors, and R is the radius of the conductor. So that potential gradient G is equal to V by R into ln of d by R. This much amount of gradient was available on the surface of the conductor. From the basics of the electrostatics, we came to know that potential gradient. Okay. So with the help of that potential gradient, we can observe what is the magnitude of the disruptive critical voltage. So the formation of the corona, as we know that it is initiated whenever this gradient is equal to breakdown strength of the air. So as we know that ionization or breakdown of the air around the conductor is initiated at a voltage called VD, disruptive critical voltage, and that breakdown or ionization is completely occurring if and only if this gradient value is equal to the gradient of the air. Then what is the gradient or breakdown voltage of the air? In general, we know the breakdown voltage of the air. What is breakdown voltage of the air? It is 30 kV per cm, and it is a peak value, maximum value. In RMS, we can write this as breakdown strength of the air. RMS value is equal to peak value by root 2, that is 30 by root 2. Its value is 21.21 kV per centimeter, which is defined in RMS quantity. In peak values, it is 30 kV per cm, whereas in RMS quantities, its value is 21.1 kV. And this value of breakdown strength of the air, 30 kV per cm, is defined at standard values of the temperature and pressure. So, what are the standard values of temperature? It is 25 degrees centigrade, and pressure is defined at 76 centimeters of Hg, that is mercury. So, the breakdown strength of the air is nothing but whenever the gradient on the surface of the conductor reaches to the breakdown value of the air, whose value is equal to 30 kV per cm peak value or 21.21 kV per centimeter RMS value. So this dielectric strength of the air or breakdown voltage of the air is defined at standard temperature and barometric pressure like 25 degrees centigrade and barometric pressure of 76 centimeters of mercury, that is Hg. Okay. The next is, if at all if the temperature and pressure are not at their standard values called 25 degrees centigrade and 76 centimeters of Hg, then there requires some correction or air density factor is required to find out the exact breakdown strength or the gradient at which the corona starts. That is given by at any other temperatures and pressures. This is defined with G naught dash. Okay. So that G naught dash is equal to actual value of the breakdown strength of the air 30 kV per cm peak value is to be multiplied with the air density factor called delta. That is, at any other temperatures and pressure, G naught dash is equal to delta into G naught, where G naught is 21.21 kV per centimeter RMS value. Then what is this delta? Delta is nothing but air density factor. Why we are calculating this air density factor? Because the temperature and the pressure are other than the standard values. Okay. Then what is the air density factor? The air density factor is given by a numerical formula 3.92 into barometric pressure by 273 plus temperature T in degree centigrade. So whenever you know the other temperatures than 25 degrees centigrade, then we will use the temperature T here, which is converted into kelvins because the given is in degree centigrade, and this barometric pressure is the other value than 76 centimeters of Hg. So with the magnitudes of this barometric pressure given and the temperature, we can define the correction factor in the air density. That air density factor delta will be used here to estimate the breakdown strength of the air, that is gradient G naught dash. Okay. Then whenever this G naught dash is observed for us, that is G naught into delta, use this formula, the basic gradient formula. What is basic gradient formula? G is equal to V by R into ln of D by R. In our previous discussion also we came to know that gradient G is equal to V by R into ln of D by R. Whenever this G is equal to G naught dash, whenever this G is equal to G naught dash, then this operating voltage we can call this R, we can define it as a disruptive critical voltage VD. Therefore VD is equal to G naught dash R into, let me write down here, VD is equal to G naught dash R into ln of D by R. If you expand that G naught dash as per this formula, we get VD is equal to G naught delta R ln of D by R. So the formula for disruptive critical voltage is G naught, air breakdown strength 30 kV per cm peak value, delta air density factor 3.92 into B by 273 plus T, R radius of the conductor, ln of D by R. D is the distance between the conductors, spacing between the conductors, and R is the radius of the conductor. So this formula, this is the magnitude of the disruptive critical voltage, assuming that the surface of the conductor is a smooth surface. Okay. So the corona depends upon occurrence of the corona, means the voltage at which the air around the conductor starts ionizing, also depends upon the surface. Okay. So this is the magnitude what we observe, VD, which is equal to G naught delta R ln of D by R with the condition applied. What is that? The conductor is having smooth surface. But in real time, in practice, at outside, in practice, you can observe the surface is not smooth and it is accumulated with dust and dirt particles, so that the surface is not smooth and uneven surface we can observe. For such a type of uneven surface, less than VD what we have calculated, at that less than voltage itself it starts ionizing. So we have to introduce a factor called irregularity factor. So this is irregularity factor M naught, which we are going to use for this formula, where the entire magnitude of this disruptive critical voltage is G naught 30 kV per cm peak value or 21.21 kV RMS, always we have to use RMS value 21.21 kV per centimeter. And next delta is the air density factor M naught. Just now we have given the real-time practiced value of disruptive critical voltage for uneven surface of the conductor also. This M naught is the irregularity factor and R is the radius of the conductor. Ln of d by r, d is the spacing between the conductors and r is the radius of the conductor. So this M naught value depends upon conductor to conductor, it varies. So let us see what is the magnitude of that M naught. Recalling the magnitude of this disruptive critical voltage, whose value is equal to Vd is equal to G naught delta M naught R ln of d by r. This is kV, kilovolts, because this this G naught, whatever we are using, is the breakdown strength of the air, whose value is equal to 21.21 kV per centimeter. Since it is defined in kVs, G naught value, the entire magnitude of this Vd will be in kVs. Means this value Vd will be in kilovolts, kVs. Okay. Out of this entire magnitude, M naught is the irregularity factor, which is less than 1, will be varied from case to case. Let us identify what is that M naught. M naught, its value is equal to 1 for a polished conductors, means for a smooth conductors, as we told in the starting. Okay, this M naught is equal to 1. Whereas M naught is equal to it varies in between 0.98 to 0.93 for a roughed surface conductors, for a rough and wires. Okay. It varies in between 0.98 to 0.93, and also this M naught will be varying in between 0.87 to 0.83, 0.87 to 0.83 for a 7-stranded cables. The cable consisting of 7 number of strands. For such a type of 7-stranded cable, the M naught varies in between 0.87 to 0.83. For large cables, more than 7 strands, the M naught value will be 0.9. So these are the ranges of irregularity factor. M naught depends upon from case to case. So M naught is equal to 1 for polished conductors, whereas M naught is equal to, it is varying in between 0.98 to 0.93 for roughened surface conductors, and this M naught is considered to be varying in between 0.87 to 0.83 for 7-stranded cable, and the cable whose number of strands are more than 7 for large cables, its approximate value of M naught is 0.9. So that finally the disruptive critical voltage Vd is equal to G naught 21.21 kV per centimeter delta air density factor, which is equal to 3.92 into B by 273 plus T. M naught irregularity factor can be selected one among these. R radius of the conductor. Okay. Ln of d by r. D is the spacing between the conductors. R is the radius of the conductor. In to be more specific, in order to have a correct calculations, one important precaution should be taken. That is, G naught, if you verify here, it is defined as 21.21 kV. It's an RMS value. Purposefully we selected as an RMS per centimeter. So this value is defined for centimeter length. Means this G naught is defined for centimeters. Since this G naught is measured for centimeters wise, the radius R should also be defined in centimeters. Keep it in mind. Okay. As our regular practice, always we will consider the meter in meters. But here it should not be considered in meters, it should be in centimeters, because already G naught value what we took is in centimeters. Okay. Here in the ratio, it is your wish. Can be taken in centimeters or meters. Okay. So this is about the disruptive critical voltage calculation. And if the operating voltage is beyond this disruptive critical voltage and increasing, then complete ionization of air will take place, so that air around the conductor completely break down and a movement of electrons in the form of a spark appears in the air between the conductors. So such a phenomenon is identified as luminous glow, which the corona can be visualized. So the voltage at which glow appears is known as visual critical voltage. Visual critical voltage. So let us see the calculation of that visual critical voltage. In general, whose value of that VV will be greater than VD. Okay. So coming to our next discussion, as I told you, this is visual critical voltage, VV. What is the definition of the visual critical voltage? It is the minimum voltage at which the visual glow of corona appears. Visual glow of corona appears. So it is the minimum voltage at which the visible corona occurs or begins is known as visual critical voltage. So based upon the empirical formula in the experimentation process, the visual critical voltage VV, in general VV value is greater than VD. So the magnitude of that visual critical voltage VV is given by its empirical formula, whose magnitude is equal to G naught delta MV R into 1 plus 0.3 by root of delta R ln of D by R, whose unit is kV per phase, for each phase, and it is also defined in kVs similar to VD, and it is also defined in per phase quantities. Okay, so here the terms are G naught, as we all of us familiar, G naught is the breakdown strength of the air, 21.21 kV, 21.21 kV per centimeter, and this delta is equal to 3.92 into B by 273 plus T, air density factor, and this MV is called as, it is different from M naught. Previously M naught is irregularity factor for finding out the disruptive critical voltage based upon the surface of the conductor. Okay, but here MV is called as irregularity factor for visual corona, and R is the radius of the conductor, delta is air density factor, R is radius, B is distance between the conductors or spacing between the conductors, R is radius of the conductor. So this is an empirical formula, directly we can use for our problems, right? So coming to the next, yes, the magnitude of this MV is important. Similar to M naught in the case of VD, MV should also be defined for different case studies, where MV is equal to, it should be taken as 1 unity for polished conductors. So for polished conductors we can observe that the MV value to be 1. And MV range varies in between 0.98 to 0.93 for roughened wires, similar to the previous case, 0.98 to 0.93. And for local corona and general corona, for local corona we will take the MV value to be as 0.72. These are the magnitudes of the MV for different cases, and formula is visual critical voltage VV is equal to G naught MV delta R into some factor, that is 1 plus 0.3 by root delta R into ln of D by R, whose unit is kilovolts per phase. Okay, so this is the visual critical voltage, which will be in general more than the disruptive critical voltage, right? And this is the magnitude of the MV. In the previous discussion, we came to know that operating voltage, whenever it is greater than VD or whenever it is equal to VD, that is gradient equal to VD, obviously the ionization starts. Whenever the operating voltage is still beyond that VD and reached up to VV, the visual corona occurs, that is luminous glow appearance can be observed around the conductor. Now, Because of that corona existence, which is accompanied with three features, they are luminous glow, hissing noise, and production of ozone gas. These three leads to the formation of corona, and that corona will discharges its amount of energy in the form of sparks, in the form of heat, so that we can say that some power is wasted because of this corona, called as power loss due to corona. So our next topic what we are going to discuss is power loss due to corona. So the scientists has done their research work in finding out the magnitude of the power loss by conducting some experiments in the laboratory. So one of the scientists called Peake. Peake is a scientist conducted the experimentation and found an empirical formula for the power loss due to corona. So as per this Peake's, according to the Peake's, the corona loss is given by a formula P is equal to 241 into 10 power minus 5 into F plus 25 by delta multiplied by square root of R by D V phase minus VD whole square. And this power loss due to corona is observed in kilowatts, observed for kilometer length in each phase, per phase. So the unit is important. It was measured in terms of kilowatts for a length of 1 kilometer for one phase. The magnitude is 241 into 10 power minus 5 into F plus 25 by delta into square root of R by D into V phase, operating voltage V phase minus disruptive critical voltage whole square. This much amount of power is observed, whose unit is kilowatts, observed for 1 kilometer length in each phase. Empirical formula. Okay, and next other scientist called Peterson. This is the Peterson's observation. The same corona loss is given by this magnitude of the value 21 into 10 power minus 6 F into V phase square by ln of D by R whole square into F. This F is a factor which varies according to the ratio of V phase to VD. Okay, which will be given prior to us. So in general, it is not frequently used, whereas this formula is used frequently because it is nearer to our real-time applications. Even though it is an empirical formula, it is nearer to our real-time applications. So this is about the power loss. In today's class we have seen the formulas and how to calculate the disruptive critical voltage, visual critical voltage, and power loss due to corona. So let us see a mathematical problem. If you go through the problem, the line is 132 kV operating for a frequency of 50 Hz, and it is a three-phase transmission line for a length of 190 kilometers, consists of three 1.2 centimeter diameter conductors. Three conductors are there, each with a diameter of 1.2 centimeters, and the length of the line is 190 kilometers. It's a three-phase transmission line operating for a frequency of 50 Hz and a line voltage of 132 kV. And these three conductors are spaced with a distance of 2.8 meters, and they are arranged in the delta arrangement, that is an equilateral triangle at the corners of an equilateral triangle. So 2.8 meters is the spacing between the any two conductors, and assuming that G naught, as already we know that value, G naught is the breakdown strength of the air, 21.21 kV per centimeter, and the temperature, operating temperature is 30 degrees centigrade. Since it is not equal to 25 degrees centigrade standard temperature, we have to calculate air density factor delta. And barometric pressure 76 centimeters of Hg. Of course, pressure is at standard value, but temperature is not at standard value. Thereby, we have to calculate delta separately, which will be included in our G naught to get G naught dash. Okay, as per our previous discussion. And irregularity factor for disruptive critical voltage should be taken as 0.86. And irregularity factor for visual corona, for local corona, it is observed to be 0.74. and for a general corona it is observed to be 0.84. Find the corona loss for fair and stormy weather conditions. This is the problem asked in a frequently. So first, before doing the problem, let us go for the given data. In the given data, it is clear that the phase voltage V phase is equal to VL by root 3. The operating voltage is VL 132 by root 3, whose value is equal to, per phase value is equal to 76.2 kV. 76.2 kV. It is phase value, V phase. 132 by root 3, if you do it, you can get the value 76.2 kV. It is one of the given data. And the frequency F is equal to 50 Hz. It's a three-phase transmission line with a length of L is equal to 190 kilometers. This is another given data. As I told you, there are three conductors with each having a diameter of 1.2 centimeters. Means radius R is equal to 0.6 centimeters. Here I am not converting into meters, as I told you previously. The G naught value is defined for 1 centimeter distance, 21.21 kV. See here, 21.21 kV per centimeter. Because its magnitude is defined for 1 centimeter, all quantities I will prefer only to be taken in centimeters. Okay, R is equal to 0.6 centimeters. And next, spacing between the conductors, capital D is equal to 2.8 meters. So that it is equal to 280 centimeters, as 1 meter is equal to 100 centimeters. Then it is arranged in a delta fashion with the given values of G naught. Now I want to calculate the disruptive critical voltage VD, whose formula is G naught delta M naught R ln of d by R, whose unit is kV per phase. Okay. So before to use this formula, I want to calculate delta, whose value is 3.9 into B by 273 plus T. Let me calculate that. Its value is, on substitution, 3.92. The barometric pressure is 76 centimeters of Hg divided by 273 plus temperature in degrees centigrade, that is 30, given in the problem. So operating in the calculator, you will get the magnitude of this delta as 0.97. 0.97. Okay. So use that delta here and substitute to get the value of VD per phase value. G naught value 21.21 kV multiplied by delta value 0.97 is to be again multiplied with the irregularity factor M naught. 0.86 is M naught multiplied by R value, radius 0.6 centimeters. I have to put it in centimeters. That is why it is 0.6 into ln of d by R. The distance between the conductors is 280 centimeters divided by 0.6 centimeters. If you operate entire thing in the calculator, and you may observe the disruptive critical voltage to be as 65.2 kilovolts observed for one phase, per phase value. 65.2 kV per phase. This is the disruptive critical voltage. And the operating voltage per phase value is 76.2 kV. Okay. And next we have to calculate the visual critical voltage. Formula for visual critical voltage is G naught delta MV R into factor called as 1 plus 0.3 by square root of delta R into ln of d by R, whose unit is kilovolts per phase. Kilovolts per phase. So let me substitute all the values so that VV is equal to G naught value 21.21, delta value 0.97. Previously calculated our delta value, it is 0.97 into MV value. As in the problem we have observed that the MV should be taken in two case studies. For local corona it is 0.74. and for general corona it should be taken as 0.84. We have to calculate this VV in two cases, local corona and general corona. So for local corona, as I will take this as 0.74 for the first case, multiplied by radius 0.6 into 1 plus 0.3 by square root of delta into r 0.97 into r value 0.6 into ln of d by r. D is 280 centimeters, r is 0.6 centimeters. If you do all this calculation in the calculator, then you will get the visual critical voltage as 78.2 kV per phase. Per phase is important. This is for irregularity factor. This is for local corona with an MV value of 0.74. 0.74. For the next value of MV, whose magnitude is 0.84 as a general corona, we have to calculate VV. So now the magnitude of VV is G naught as per formula 21.21 is to be multiplied with delta 0.97 MV. Now MV is 0.84 multiplied by R 0.6 into 1 plus 0.3 by square root of delta R into ln of d by r 280 by 0.6 centimeters. So this is for general corona. You can observe that VV as 88.8 kV. 88.8 kV per phase. This is for general corona, whereas this is for local corona. And VD voltage already we got it. VD value is 65.2 kV per phase. Okay, these are the three magnitudes of VD, VV for local corona and VV for general corona. So we use that VD value in the estimation of the power loss. Now they are asking us to find out the power loss due to corona under two weather conditions: normal phase weather condition and stormy weather condition. So first let me calculate for phase weather condition. As per the formula of empirical defined by the scientist Peak, the formula for the power P is equal to power loss due to corona is 241 into 10 power minus 5 into F plus 25 by delta into square root of R by D, V phase minus VD whole square, whose unit is kilowatts per kilometer per phase. So as per our calculation, let me do for phase weather condition. In phase weather condition, directly I will substitute the magnitudes. 241 into 10 power minus 5 into frequency is 50 Hz plus 25 by delta value 0.97 into square root of R value 0.6, D value 280 centimeters into V phase 76.2 kV minus disruptive critical voltage 65.2 kV whole square. So doing this in the calculator, for each phase what we can observe is 1.0437 kilowatts we can observe for a length of 1 kilometer for each phases. Now the total power loss due to corona is given. As we know, the length of the line is 190 kilometers in the given data. As we know the length of the line to be 190 kilometers in the data. So I will multiply it with 190 multiplied by 3 phases. Okay. So 3 into 190 into 1.0437, so that we will get a magnitude of 594.9 kilowatts for entire 3 phases. This is the power loss due to corona for phase weather conditions, normal weather conditions. Also they are asking us to find out for stormy weather conditions. Under stormy weather conditions, the same formula is applicable, whose value is 241 into 10 power minus 5 F plus 25 by delta square root of R by capital D, V phase minus VD. Here the VD must be multiplied with 0.8 times. 0.8 times that of VD, because under stormy weather conditions, as the atmospheric conditions are not at their standard values, for low value of the disruptive critical voltage, the air starts gets ionizing only for a percentage of 80% itself. Okay, that is why 0.8 is to be taken here. So substituting all the values, 241 into 10 power minus 5 into 50 plus 25 by 0.97 into square root of 0.6 by 280 is to be multiplied with 76.2 minus 0.8 into disruptive critical voltage 65.2 kV whole square, whose unit is kilowatts per kilometer per phase. Per phase is a value. So substituting in the calculator and finding out this magnitude, we get this magnitude as 4.985. This much amount of kilowatts you can observe for a length of 1 kilometer for each phase. Since we are having 3 phases, to get the total power loss due to corona, we have to multiply it with 3 for a length of 190 kilometers. Is to be multiplied per phase value as 4.985. Then you can observe this much amount of power loss in your calculator, whose value is 2841.45 kilowatts. Okay, this is under stormy weather condition. So let me conclude today's class. So the power loss due to corona under stormy weather conditions is much more, whose value is 2841.45 kilowatts. Previously we calculated the same power loss due to corona, whose value is equal to 594.9 kilowatts under fair weather conditions, normal temperature and normal pressure, atmospheric conditions. And here this shows the calculations of the visual critical voltage for an irregularity factor of 0.8 for considering as general corona. And for the local corona, we have observed this VV value with an MV value of 0.74. All this is possible because of the disruptive critical voltage, whose magnitude is 65.2 kV. So in this class, we have learned what is disruptive critical voltage, what is visual critical voltage, and how to calculate the power loss due to corona with a simple problem also. Thank you.